This is very basic stuff. You probably have learned it in school. I'm just covering it because I will repeatedly use these things, especially in the analysis. And some of you had questions as to how all this analysis will be useful. So some of you had questions, especially those who are doing numerical analysis. I think this part you may be already knowing, but how to use what I'm going to say now for the analysis, if you see, you will understand why this stuff is relevant to you. Right? So you may already know how to do integration with some of the numerical analysis tools. But I think the main question, and I think it's a good question, right? And it's one that I often get from reviewers when we try to publish these papers is, oh, the numerical analysis people have looked at this for many years now on how to do these integration and so on. Why is it different? And as we spoke this morning, the two main differences are, one, numerical analysis was designed to work when you don't know much about the data. Right? So it is somehow a worst case approach. The second thing is it evolved in one dimension. And it has been extended, but primarily the analysis tools were one-dimensional, unidimensional, and now people have developed some extensions in multiple dimensions. So the main thing now is what is relevant today is that we have knowledge about the data, or at least we have data, and we want to ask similar questions to what the community asked, but with some additional information about what the data will look like or what is the distribution of the data. So I keep using these terms, distribution and things like that. So I thought I would like to clarify, right? So first, maybe let's talk about drawing a random number, right? So can someone guess, how will you draw a random number? So if I ask you, generate a random number, right? How would you generate a random number? If you had a die, you would roll it and say, oh, it's hopefully random between 1 and 6, integers, 1 to 6. But if I didn't have anything and I asked you to write a C++ or a MATLAB program or whatever language you want, or even simply pseudocode algorithm to generate a random number. So your function might look something like this, right? So let's say we want to generate a double, and let's say we have right? And this, let's say this is our function. Now, what is the code you put here? Can somebody guess what you might do? Yeah, so obviously there is, so obviously what you could do is simply call one of the libraries, right? So a lot of libraries will provide you with a rand. So for example, you may have, I don't know what algorithm. So this is a standard call. So if you are in C++, then you would include some header, I don't know, C or stdio or something like that. Or even random in C++ 11, you can include the random, right? You could, in your C++ program, you could include some library like this. You make a call, and that will give you a random value usually between 0 and 1 as a double. Some strange systems which were used before will give you a random integer between 1 and some very large integer they used to call rand max. So your program before, you will probably recognize this, right? You get an integer. It didn't even give you a double. It would give you some integer value. And to generate the double, you will divide. So you would get y equals some rand integer, and then divide y by rand max. But then you have to convert it to a double and all that stuff. And in the end, you'll get something between 0 and 1, or as close to 0 as possible. Right? So these are different ways you can use libraries to generate random, right? That gives you a number between 0 and 1. Then it's pretty straightforward, right? So you can simply say multiply. So if you get y equals rand 0 between 0 and 1, then you can generate z equals y plus, y times p minus a plus a, right? So if you do this transformation, that's a cheap trick. Y b minus a will be in that interval, and then you add a to get it to store. So this will give you a number. But the question is, how do these guys generate this random number? How do you think? So it's not an easy problem, right? And there have been corporations like Rand Corporation, for example, right, that were built out of this problem of how do I generate a random number, and it's not at all an easy problem. Today we can consider it reasonably solved because whatever you do, this algorithm somehow comes up with what might be a random number. So in theory, when we say random, what we actually mean is we're using some pseudo-random number that comes from this. But for all practical purposes, we can consider this to be stochastic, in that even though this will, actually what's interesting is if you run this program twice, you will get the same number, right? And that's because all these sequences, these pseudo-random sequences, are generated using one fixed value called a seed. These things are not very relevant for us, but what I'm trying to say is because of this process, you needed to do something earlier called rand seed. So before you call myrand in the main program, you had to call something like this. So the main program would do something like seed random first, right? This is not exact code. I'm just writing it so you can, and then call myrand. And say 5 to 6, you will get a float if you want to see. Now, once you randomize the seed here, there was another algorithm that would pick a random seed, and for that, you would give it something like the current time. So once you did that, then every time you generate a random number, the seed would be the current time. Hopefully, it has never happened before, and your system clock has been faithful. So then you would get a random, unique random number every time you run it. Problem with this is it's very hard to debug. So if you run into a case where there's a seg fault, for example, something failed after you did this, recreating that failure is a nightmare, right? It's a zero probability event that you get back that particular sequence of random. So many people, when they debug, they remove that and then debug. Anyway, so all of this, the reason I'm bringing all of this up is all the time we say random when we talk about probability in a computational framework, we are talking about using pseudo-random numbers from these kind of libraries. Again, numerical analysis people came up with algorithms to do these. Right? And today the question is probably very rare, right? Like very few people are interested in how to do this. And we could spend 5 days talking about how to do that. It may not be that relevant because there are hundreds of libraries out there that allow you to do it. Okay, so now let's say I repeat this 1,000,000 times. I generate 1,000,000 random numbers with my rand, and then I plot a histogram. Right? So I plot a histogram of the 1,000,000 numbers. Then what I would get is something like this, right? So they will roughly be the same number. This is the maximum value of 1, this is 0. Which means my random number generator is giving me something that's uniformly distributed. This is what I meant by uniformly distributed. In the interval 0, 1, right? Now, if I run another 1,000,000 numbers, then the histogram will change slightly. Some of these will go down, some of these will go up. If I do this several times and average all the histograms, then ideally I should get something perfectly flat, right? And then you will get some for each of these bars. You can calculate standard deviation, and you'll get some error bars that tell you how far away you were from uniform. Okay, so now let's say I don't want to generate uniform numbers. So remember when we did this Monte Carlo example this morning, we generated uniform numbers, and some Sunil, I think, right, suggested that we can maybe exploit priors if we know something like we did for the polynomial case, when we knew it was quadratic, immediately we used that, right? So, but how do we do that for stochastic samples? Right? Suppose now if we go back, so if we go back to our previous example, I'll just draw this again, and we say that we know that our function looks something like this, okay? Then what we can do is now we can think of maybe what if we generate, so somebody suggested we can generate more samples in the area where the value is high, right? So now we are making a big shift. We are no longer going to draw uniformly distributed samples, right? So earlier we said something like this, right? We said xi was drawn uniformly in 0, 1 in our previous example, right? Now we're going to draw yi distributed according to some g of x. And let's say we want g of x to be a, let's say we want g of x to be a Gaussian. For example, it could be a Gaussian because the Gaussian is even, right? Now this here means that we are using the distributed as. What does this mean? This means now if I draw 1,000,000 samples from here of yi and plot a histogram, I'm not going to get uniform. Instead, I will get a histogram like this. Right? For samples from G of x. Right? Is that visible at the back? Yeah. So that is going to be the histogram. So that's what I mean by non-uniform samples. Now we come back and say, okay, that's fine. Anybody can do this, right? So now I can have a different estimator, mu2, which is also using n samples, which, okay, so this may be confusing, right? It's not 2n samples. Let's call it mu2 like this. It's a second estimator. Previously we had mu. Let me show you that. So here we had mu where we were averaging n, right? And we still are going to average over n. But the question is, if we, let's say, do this. Right? Then first question is, do you think you will still get the right answer as n tends to infinity? And if not, then why not? Or if yes, why yes? Why does it not make a difference? And we change the distribution. Does anyone have intuition on this? Okay, so first of all, the fact that we have changed this distribution means now there are very few random numbers that are going to be generated here, this part of the domain, right? Which means whatever values we sample of the integral, right? Remember, this is a distribution, right? It's not a function directly. So what's going to happen is I may generate lots of samples here, maybe some samples here, and almost no samples on that side, right? Okay, so all our values of the function are going to be here, mostly, right? What that means is if we average this, we're not going to sample this part of the function space at all, or maybe very, very less, which means our answer is going to be biased towards this. So let's do this. And we are no longer going to get the answer that we expect. Right? So how can we then compensate for this? So the natural way to compensate for this I will call it some other estimator, is to do this. I made a mistake already. So it's just a notational mistake. I should have called this yi, because x is uniformly distributed. Right? F of xi divided by n is still the same estimator as before. Now we have yi is the one that's non-uniformly distributed, right? This one. Yeah. So if I write it as yi, then it's biased. Now, if I have some other estimator, I just call it that, cy, and I do this. So we still normalize by the number of points. Now what I'm doing here is I'm saying I'm not only going to take the function of the value y, I'm also going to divide by whatever the distribution at that point. So if I choose this point here, then I'm going to take g of y here and divide it. What that does is it makes this weight of the function uniform across. So even though I will only very rarely sample here, because g of x is so low there, if at all I happen to sample, I will tell my estimator, you should give a lot of importance to this sample. Because you're very rarely going to see this space of the function, you need to give it a lot of importance, right? Which means I will have maybe one sample there. This guy here will suddenly get weighted by 1 over g of x there, which is extremely small. So the contribution to that summation will be very high. And what this does is it gives us an unbiased estimate. Okay. Now the reason I called it IS here is that it is called importance sampling. Right? This is something you would have probably seen in many places as well as a term. And the reason it's called importance sampling is what you're saying is give this different importances depending on what g of x is. Now if you look back and if you change g of x to be flat, then your importance function is simply going to be a constant. Right? So if you have a 0 to 1 and it's a PDF flat there, it needs to integrate to 1, which means the value is 1. So everything becomes 1. Okay, so that is what is called importance sampling. And it is just playing. So if your prior is known, if you think your shape is a parabola, then you can appropriately generate samples. Now, if this is actually the most interesting thing about importance sampling is if you know how to generate samples from f of x itself. So rather than choosing g of x to be different from f of x, what if I sample from g of x from f of x itself? So if I'm able to draw samples from f of x, then what is my estimator? Can anyone tell me? So let us blindly replace this in the previous formula, right? What do you get then? Then you get 1 over n, summation again, f of zi, because that's the new variable, divided by f of zi, because we have drawn directly from f, so g is f. And then it's interesting because we get back, that's a bit strange, right? Why is that the case? It's really bizarre that we said it's an unbiased estimator, yet if we simply plug in f of x as g of x, and we follow everything through, we don't get any integral at all. We just get 1. Because f of x cancels here, and then you have 1 over n, sum of I equals this. This becomes n by n is 1. So you just end up with 1. The reason for this is anytime we say distributed according to, this needs to be a what is called a probability density function. You will not imagine the number of hours a PhD student who works in these areas spends debugging this. Okay, so if you are ever going to code, personally, I myself have probably spent over 100 hours at various points in time because of this subtle distinction, which is that if you want f of x to be a probability density function, what is required? It is required that the integral of f of x over whatever domain, in this case 0 to 1, equals 1. So by doing this, what you have simply said is the integral of f of x is 1, which by virtue of being a PDF, it needs to be anyway, right? So what is very important is generally when you are drawing samples, so let's say you're given a distribution of traffic, distribution of photons, distribution of whatever points, and somebody says, here is the distribution of points, right? It's very easy to confuse what the density of points is with what is the probability density you need to sample, right? And the difference is actually very minute. So if f of x did not integrate to 1, then you can make any function h of x a PDF, right? All you have to do is construct hp of x equals h of x divided by integral of, right? So this is called normalization, and in this case 0 to 1, right? So given any function f, if you're able to normalize it, then you can calculate the integral with 0 samples. That's a paradox, right? Because obviously if you want to normalize it, you need to calculate its integral. This means that what we have done here, which is called, this is called perfect importance sampling. This in practice is never useful. In theory, it is the ideal estimator. You don't need any samples. You get 0 variance, 0 error, and you can calculate. But in practice, it means you should know what the integral of f is to normalize. Either f is already integrating to 1, in which case you don't need to do anything, or f is integrating to some other value which you have to calculate in the first place before you do this, and so you're left with the chicken and egg problem, right? So perfect importance sampling is a theoretical idea which is nice because it verifies that everything else is true, right? So it tells us that this is unbiased. So in terms of theory, it's useful to understand. In terms of practice, it's completely useless, right? But what we have learned through all this is what is a probability density function, what it means to draw samples, what it means that for a sample to have a parent distribution. So people would call what I've been calling distributions, people would call parent distribution, also known as parent distribution. Okay, anyway, that was a long, windy route to just tell you that anytime you see this sample, remember to normalize. If you don't normalize, you will be off by a factor which is an integral. And in case it happens, as in my first paper, that integral is hard to compute, then there is really no point adopting that sampling strategy. Because in the end, you will end up having to compute some other integral, which will be probably more costly than the integral you started off in the first place. Right? So that is a very tricky thing in Monte Carlo, which is that you need to always keep an eye on where your random numbers come from and what their distribution is. So it's very easy for us to say x is uniformly distributed. But if x is a photograph coming from a collection on Facebook, and Facebook wants to do some analysis on this, they have no guarantee that it's going to be uniform. They don't even know what distribution it comes from. So they may take millions of images, do that histogram that we talked about, see what the distribution looks like. Then they have some idea of what this is. Again, this is all prior, right? So in this case, if you have a Gaussian prior, the advantage is you can sample easily from a Gaussian prior. Now, if this prior gets more and more difficult and generating these samples becomes a pain, then there's really no advantage to using the prior. So the trade-off in whatever application is how do you choose what to sample from, right? And how do you reconcile this? Yeah. Okay, no problem. What is your name? Sorry? Vikas, have you already registered or just today? You registered. Okay. Could you add your email, please? Where is that email? Yeah, you can add it and I'll take it from you later. You can take it to your list. So, so knowing this distribution is one thing. Being able to sample from it is another. Sometimes, as I said, your samples may naturally come from some distribution. Sometimes you may have to choose a distribution as a compromise because it is easy to sample from. And that really depends on the application. Okay, so now through this, I think you should have an idea of now what is a parent distribution, what is a distribution, what is drawing a sample from a distribution mean. And we also had some idea of how do you generate this importance sampling estimator, right? And that is why I called it IIS, mu IIS, just to distinguish. So I'll give you a link to some notes which will explain all this stuff. But for now, that mu IIS is set. Okay, so now how do you think mu IIS compares with mu, just the plain sampling? Do you have any guesses on? So let's go back to this. We know that the standard Monte Carlo gives us this. What would you expect the mu IIS curve to be? If this is mu m, where would you expect mu IIS? Any guesses on how it could? Is there anything you can say for sure? Regardless of the prior, regardless of your function, regardless of any shape that you know, what can you say? So the thing you can say about importance sampling is regardless of any of these factors, it is going to be parallel to this. So the rate of convergence will not change. There will be no benefit at all. If you shape your prior with very, very carefully chosen distribution, you can maybe achieve this, right? And if otherwise you're somewhere in this space here, right? So mu IIS could be here, say best case. Well, the best case is 0 with perfect importance sampling, but we've already established that that's not useful. So the best case where you can actually do something may be here. And the funny thing is, your worst case is unbounded. If you choose a bad parent distribution, we already saw, right? Because we are weighting by the reciprocal of the density, if you choose a density which achieves a very low value where the function is very high, you may very, very rarely go to that space and you'll pay a very high price because your error will be very high. Even though it will converge and give you an unbiased estimator and all that, you will need a very large number of samples to get error to somewhere usable. So again, this is an example of using a clever strategy, spending a lot of time thinking about making it clever, but ending up with the wrong importance function. It will end up doing something like this, right? So maybe, yeah, questions? Okay. So that is importance. Importance sampling is a very commonly used strategy as well. But the important thing is it does not change convergence. And then how could you change convergence? Now let's say I don't want to use importance sampling. Do you have any ideas on how I can make this better in terms of slope? So I showed you several algorithms that were changing the slope. Can you guess how you could change the slope? Right. So, yeah, any guesses? So then how can you change the slope? So let's think in 1D, right? So you have this domain, you get random samples like this, right, which are uniformly distributed. How could you make them better? Let's say we want to keep the samples uniform. What is the first problem we see with uniform samples? And you can do this in the lab today. So if you just call random 100 times and you plot the locations where the random numbers are, obviously it could be all over the domain, right? So what is the problem with this? The problem with this is, you see, even in my totally arbitrarily chosen point set, there is a very large part of the domain here which doesn't have any samples. And that could easily happen even if you draw 1 million samples. There may be a large part of the domain where there's no samples. And to your bad luck, if the function happened to reach the peak there, that particular estimate that you got will not be a good estimate. You will get a lot of these low values. You may underestimate your integral because you didn't have any sample here. Of course, it's stochastic, so you would have done it a second time and a third time, and in the end, you would have got a reasonable estimate. But the variance of the estimates would go very high because there's one very low value, right? So this is a big problem with Monte Carlo. In general, the problem is the variance depends on many things, including spaces. So one thing that people have strived to do over many years now is try to distribute these samples. So I'm going to use distribute slightly differently now. It is always uniform in this particular example, but I want to make sure that all parts of the domain are covered, right? And that is called equidistribution, which unfortunately also has the word distribution in it for historical reasons. And now people try to use it less. But what we want to do, and the term I prefer, is arrange. We want to arrange samples without changing their distribution so that we can cover parts of the domain that might not otherwise be the case. So what would be the simplest strategy? Yeah, so that is very similar to the strategy you proposed first, right? You said take a random value and then split it into finite. Instead, we do the opposite. What we will do is we will do what we might have done for the Newton Cotes-Simpson rule or whatever. Split this domain into equal partitions and then draw random inside each. Okay, let's think we are going to do this. Then this is called a stratum. So we stratify the domain. So partition the domain into strata. Each is called a stratum. And we're going to draw a random value in each, or maybe different random numbers. We could do n1, n2, n3, n4 values in each, or just one sample in each. Now, if you do one sample in each, what will happen is you're guaranteed that this part of the domain will have a sample. And by controlling how many partitions you make, you can sort of guarantee that regardless of what your this function does, to this resolution, you're always going to guarantee a sample. And in terms of distribution, you have not modified anything. They're all still uniformly distributed within each. And you're going to draw one sample necessarily from all of them, which means the overall distribution of the samples hasn't changed at all. We're still going to have n samples that are uniformly distributed, n equal to n1 plus n2 plus n3 and so on. Right? And we can prove this. I'm not going to prove it now. And you can prove that if you draw samples like this, you still get an unbiased estimate. Any questions? What's the advantage of this, though? The advantage is by guaranteeing this miraculously, and if you look at the proof, you will see why mathematically, instead of this, you end up getting this. Right? So Suddenly we have improved convergence. And what you can say is as you increase the number of, and what your improvement in convergence is depends on the dimensionality. If you're in 1D, you get a very big advantage. If you're in 2D, you get a slightly lower and so on. And you can easily see intuitively the reason. And mathematically, if you derive it, actually, it will be very easy to see why. So we can say that stratified sampling with one sample per stratum converges faster. Of course, now if you start playing around with strata, where you put the strata, right? Again, this was all for equal strata. And then your analysis comes in, right? Again, numerical analysis comes in because you ask the question, oh, what if I don't spread it into equal strata and I make some big and some small? The question is, how are you going to do some small and some big? And this is a very important concept that was born from survey sampling. Right? People wanted to know things about, let's say economics. During the war, they wanted to know how to improve certain conditions. As I said before, it's very difficult to find a uniformly random person in the community, in the population. So they stratified the population, say based on income, based on many various factors. And from each strata, each of the stratum, they took some survey, made estimates within there. So this is going to be an abstract figure. And so if that is the universal set of all people, what they did was they said, okay, so we will stratify this into some partitions, and then we will sample people here, use these samples to estimate the mean here, take some samples here, get mean mu2, and so on. And then the global mean, we will take it as some weighted sum of all of these means. Now, how do you find these weights? That's a bit tricky. So there you need to be a bit careful. You need to know how many people are in this stratum, how many of them. That again requires some sampling. But once you do this, the advantage is that because your function is relatively smooth in this stratum, the assumption is that people who are in this particular partition, whatever it is, whether it is based on income, whether it is based on your profession, or whether it's based on the state you live in, for example, in India, or climate conditions, all that stuff. This partition is made on the assumption that the variation inside the partition is very low, right? So we are assuming that your function is like this, maybe a bit all over the place, but we are assuming that, in this partition, the variation is low. So we are partitioning this into that. And then we will sample in each of these partitions to estimate the mean and then combine all of these. Obviously, you can see already that your weights need to depend on how big each of the partitions are, right? It's a bit like importance sampling in that if you stratify here, even though you have a small part of the domain, your integral is going to be large and your contribution. So that is stratified sampling. And you can extend this to higher domains. And it turns out that it's a very powerful concept that is used today very widely in many fields, including computer graphics. Okay, I think that's enough about for now. Any questions? Has any of you seen this before? Stratified sampling or importance sampling? Okay, so small useless. Okay, so now we will quickly do some Fourier stuff and maybe then head over. Yeah, sorry. No, they don't have to be in. So the strata doesn't have to be equal. I started with a very simple example where the stratas were equal. Yes. Yeah. So there's a lot of theory of this, right? So I'm not meaning to cover depth, but yeah. So the reason I'm doing this is now you can look on Google for stratified sampling. So normally with these things, the problem is to relate your problem with something else. You need to know what that's called, because very few papers will tell you this, right? So if there's someone who's used stratified sampling, they're not going to explain this to you. They will simply say, oh, we use stratified sampling with these strata, right? Now you can Google and see what it is. So yeah, there are ways to optimize. Again, if you don't know the function, there's really no hope of optimizing, which is why this strategy of equal strata, right, with one sample. So in this case, this is called, does anyone know what this is called? This is called jittered sampling. Because another way you can think about this is to take your regular grid, right? Uniform regular grid, which we did for the polynomial thing, and simply perturb each. In practice, that is how you will generate this. You will get your regular samples and simply perturb each sample by a random value minus W over 2. So if the width here is W, you will perturb it from minus W over 2 to W over 2 around that mean, right? Yeah, so the way you would generate jittered sampling is you would take what is called a Dirac delta or a Sharp function, which means previously you were doing this. You will take each of these and perturb it in the x direction by a value that's half the distance between these. Right? That way you're guaranteed to cover the entire domain, because every sample will go from its minus half to plus half. Or you can think of it from minus this to this, or here to the next one. Either way, whatever you do, you're guaranteed to cover the entire domain. You're also guaranteed to be uniform because you're perturbing all of these uniformly randomly. You generate a random value between minus WO2 and WO2 and add it to whatever you had there, right? So you're perturbing that sample here. And in many signal processing applications, actually, when you measure, so let's say a microphone is measuring an acoustic signal, it will very rarely measure it exactly at t 1 second, 2 seconds, 3 seconds. There will always be some lag, or it will do it early. So in practice, any signal we record has this artifact, which is called jitter. Right? Jitter is unwanted in signal processing. Nobody wants it. We want to measure things exactly at the times we think we're measuring them, but we have no escape. There's always some amount of jitter. In this case, we're using jitter. We're intentionally taking samples, jittering them to get some advantage. The terminology jitter stuck because jitter has been known prior to people using this. So we would take a regular grid, which is very easy to generate. It's just 1 over n, if you want to think of it like that, right? And then k times 1 over n. And then take each sample and bump it by a random value, minus W over 2, W over 2. So you generate a random value. We did my rand, give it minus W over 2 to W over 2, and then add it to whatever is the k over n. That's it. You're done. You've generated your jittered samples. And for this simple strategy, you're able to get this. So what do you think? Obviously, there must be some downside, right? So what do you think is the downside? Yeah, so there are many downsides, but one of the most obvious thing is, yeah, you've shifted your regular grid. You don't know what the drawbacks are. But for integration, probably it doesn't matter because you don't need to know exactly where you measured it, right? However, if you think about what our problem was with the polynomial sampling, we couldn't scale up dimensions because every time we went up, we needed n to the d. Now, if you come back here, we're going to do this. In d dimensions, we need to necessarily have these partitions in all d dimensions, right? And as your d grows, it's very hard to partition equally in all dimensions. You will end up with a similar problem. So what you may choose to do is to stratify along one dimension, not another, which is fine, which will still be better than random, possibly. But this will result in all kinds of unequal strata, and then you have to weigh them. So you can do it, and people do it, but it's very rarely a huge win. In very, very high dimension. In reasonable up to 10D, there's still an advantage. But yeah, so that is another problem. And designing strata for a general purpose is not easy unless you already know something about the function, right? So this is a very active research area. People still don't know how to do this. So if I've given you this function and I ask you to stratify it, if you're able to adaptively come up with a stratification scheme, that is something that I think all communities would appreciate. But it's not easy, especially in high dimensions, because you can imagine now if you have this in 5D, we don't even know what form the strata should take. Right? There'll be some polyhedra, they could be concave, they could have all kinds of weird shapes. So it's very hard, first of all, to even find a representation for this strata.